Okay, so we've seen how the GCMs handle the actual air. They use the laws of radiation, heat flow, thermodynamics, and they use the Navier-Stokes equations of fluid mechanics to see how one cell pushes another, how mass flows from one to the other. Then another crucial thing, though, is to deal with the surface underneath the model, the land surface or the ocean surface. And this is going to be absolutely crucial. So we look at the layers of air touching the land, and we can see what happens here. One thing is, how much sunlight does the land surface absorb? Now that depends what it's covered in. If it's ice, very little. The sunlight just bounces off. If it's covered in trees, it absorbs most of the light. So you've got to know what the vegetation level is. But you've also got to figure in how that vegetation is going to change. For example, if your model says that you get no rain in a forested area, then eventually the trees are going to die or burn, and you're then going to get something else which might reflect more light. So you've got to factor in how the weather affects the vegetation as well as how the vegetation affects the weather. Then you've got evaporation. If there's water on the surface or wet ground, it's going to evaporate and put water vapor in, which brings both energy and liquid, which can then rain down somewhere else. To understand that, you have to know what happens to the water when it lands on the surface. If the water lands, does it flow away in a river? Does it seep into the ground? Does it evaporate immediately? Because that's going to determine how much evaporation you're going to get, which will also affect the weather. And also you've got to look at, do you build up swamps or ice or snow? Is the precipitation coming down as snow, and is it cold enough for it to stick as snow and build up? Now, all these parameters are based on real field measurements. There are scientists who go out and actually measure, okay, what is the radiation being absorbed by this tropical rainforest or pine forest? What is the evaporation rate? How does it vary depending on the wind? How does it vary depending on the humidity? So all these parameters that go into the models are all based on real experiments. People have gone out there and said, okay, if you have a desert and it rains, what happens? How much of the water can then evaporate? How much sinks and how much flows away? All these parameters which have to go in the models, they're not numbers they make up. These are real numbers based on real laboratory, well, not real laboratory, real field experiments. Perhaps even more crucial than the interaction with the land is the interaction with the water surface. Now, partially this is things like evaporation or freezing, like is the water frozen, like the North Pole? And again, laboratory measurements have said how long you need to be below zero before the ocean starts to freeze, and there's plenty of data about that to base it on. Also the evaporation rate, and again there are laboratory measurements, or laboratory, field measurements, so people have measured the evaporation rate depending on the wind speed and the temperature and the humidity. So those all go into the models to work out how much water is sucked up and whether the sea is frozen. But then you get the wind, and the wind pushes waves and it pushes surface currents. So if you have a trade wind, a long wind over a long direction, that will start water moving underneath, carrying, say, hot water along with it. You also get the cold, deep currents, which are also driven by the weather. Here's how these happen near Antarctica. What you get is you've got the water here, which is normally frozen, but you get so-called katabatic winds. The extreme cold over the ice sheets cools the air and gives you a stream of frigid air flowing rapidly down over the sea, and that actually pushes the icebergs away from the coast, leaving water along the edge, so-called polynyas, if I've pronounced that right. And this water is really crucial because you've got incredibly cold water, but with the ice being pushed away, and because it's so windy, that's causing the water vapor to evaporate. And when it evaporates, it just takes away pure distilled water, leaving the salt behind. So what you get is incredibly cold, very salty water, which is dense, and so dense that it starts to fall. So you get a cold current flowing down. And this produces a so-called thermohaline circulation, which is crucial to the world's weather system. You get warm surface currents driven by trade winds. You look at the average direction of the winds, and that pushes warm water around in various places. Most famous of all is the Gulf Stream that brings warm water from the Caribbean to Europe, which is why London is much warmer than Moscow or New York, despite being farther north. And then at these polar regions, you get the polynyas, or similar situations in the northern hemisphere, where you get cold, salty water falls and flows back as deep ocean currents. And all this is driven by the weather. It's the winds producing the pollutions, evaporating, producing the high salt, cold water to drive it, and the winds pushing the warm tropical climates. So you need to factor all these in, because ocean currents transport huge amounts of heat around, and they're also longer lasting, so they tend to set the long period climate.